All right, section 7.7, Dalton's law of partial pressures. You'll be able to calculate the properties of each gas in a mixture of gases once we're done with this. All right, Dalton's law of partial pressures basically says that the total pressure of a mixture is equal to the sum of the individual pressures of the components of a gaseous mixture. So if there are two different gases, well, gas 1 has pressure X and gas 2 has pressure Y. The total pressure for that whole system is X plus Y. So a mixture of gases follows the same laws as a pure gas that is composed of only one substance. Now, to illustrate this concept pretty simply, a mixture contains oxygen and neon. This contains oxygen at a pressure of 726 torr and neon at a pressure of 44 torr. Now, what's the total pressure for this mixture? Well, we've got our two pressures. 726 plus 44 equals 770. So that's the total pressure for that mixture, the pressure of individual gases combined. Now, the ideal gas law in gas mixtures gets a little bit more complicated, though, whenever we do something like this. The ideal gas law applies to the total pressure of a mixture of gases, P sub total, and to each of the components of the mixture separately, P sub I. Okay, so P total is equal to number of moles of the total mixture, the gas constant, the temperature, and the volume of that total system. Okay, and the pressure of an individual gas is equal to the number of moles of that gas times the gas constant, temperature, and volume of that individual gas. Now, we use that for this X sub I. That's the mole fraction, which is the number of moles of a individual component divided by the total moles in that mixture. So we're going to see this play out with a question like this. A 10.5 liter sample. Okay, so let's go ahead and start with a couple of things. PV equals nRT. R is equal to 0.08206 liters atmospheres mole Kelvin. Okay. V is equal to 10.5 liters at a temperature 292 Kelvin. This contains P sub O2 equals 0.622 atmospheres and N2 at 0.517 atmospheres. P sub N2 is equal to 0.517 atmospheres. Okay, so in this question, with this scenario, we're going to be asked a couple of different things. The first thing is calculate the total number of moles of gas in that sample. Okay, we know that we have 10.5 liters of a gas. We've got a volume. We've got a temperature, 292 Kelvin, and then we've got pressures of these individual gases. Okay, so the way that we solve this is for A, total number of moles of gas in the sample. What we need to do with that is we need to figure out the P total. Because if you look at what we have the R value, we have the volume, we have the temperature, but we have individual pressures. Okay, so what I'm going to do for part A is figure out P subtotal. And I'm going to do that simply by adding my two pressures that I've been provided with, 0.622 plus 0.517. 1.139 atmospheres. Okay. Now with that information, well, then I could plug that in and figure out the number of moles of a gas, or of gas in the sample. So I'm going to say, I'm going to take PV equals nRT, and I'm going to rearrange it to isolate N. And so what I'm going to do is I'm going to say P times V divided by RT equals N, because that's going to give me the total number of moles of gas. I've got the total pressure, So I'm going to plug in 1.139 times my volume, which is 10.5. And I'm going to divide that by 0.08206 times temperature, which is 292 Kelvin. And that's going to be equal to N, my total number of moles of gas. So 1.139 times 10.5 divided by, and here's in parentheses, 0.08206 times 292. Oopsies. Sorry, I had a calculator issue. So 1.139 times 10.5, close parentheses, divided by, parentheses, 0.08206 times 292, close parentheses. And that's going to give me N is equal to 0.499 moles of gas. Now, that doesn't tell me about one of the gases. That tells me of all of the gases in the system. Well, what do I have? Okay, now the next part. So part B of this question says, well, how many moles of O2 are present in this system? And this is really kind of a different way of looking at this question. We have actually two different ways that we can solve it. And I'm going to start with the first way. And that is simply by using PV equals nRT and rearranging, just like we did in the last question. So this is calculate the number of moles of O2 present. Well, what we can do is we can just take the partial pressure, or the pressure of O2, and I'm going to write this, N equals PV over RT. 0.622 is equal to pressure of my, oopsies, made a mistake there. I don't want to do it. Yeah, I do want to do it like that. N equals PV over RT. N is what I'm solving for. N sub O2 is equal to the pressure of O2, which is 0.622. The volume, the total volume of my system is 10.5 liters. R is 0.08206. Then temperature is 292. Solve. Notice I use the total volume of my system because that's, well, the O2 is only one of the gases in this total system. But that's fine. I'm just looking at the fraction that is O2. So 0.622 times 10.5 divided by 0.08206 times 292, and I get 0.273 moles of O2. Okay, another way that you can look at this is, so I'm going to say B take 2. This is another way of solving this exact same problem, but we're looking at O2 as a fraction of the total system. So what we're going to do is we're going to say the pressure of O2 related to the pressure total is equal to the number of moles of O2 divided by number of moles of total. And the way that we're going to set that up is we're going to plug in I'm going to write it right here, 0.622 divided by, well, do I have the total pressure of my system? I do. It's 1.139. This is equal to, let me erase this. This is equal to number of moles of O2, which I don't know. But do I know the total number of moles of gas in my sample? I do. I solved for that earlier, 0.499. So I'm going to do the algebra to solve for N sub O2. So 0.499 times 0.622 divided by 1.139. And lo and behold, my N sub O2 is equal to 0.273 moles of O2. So these are this part B down here. The purpose of this, the reason that we did it two different ways, was to illustrate that you could have used the ideal gas equation. You also could have looked at this O2 simply as a part of the whole. And by doing that, you can compare and relate the pressure of one gas to the total and relate the number of moles, or one gas to the total as well. All right, well, I hope this is helpful, and it gets a little bit trickier. I would say as long as you can understand those relationships, you're going to be in good shape. I say that it gets a little bit trickier because of the fact that all of these gas law equations, one of the things that they include is making conversions. And so just when you're on, you're working through these problems and you're like, okay, this uses torr, this uses atmospheres, you'll see a problem that gives you a unit that's a little bit confusing. You'll just have to make sure that you convert to those proper units. All right, well, I hope this is helpful, and I'll see you in the next section.